This section contains 4 distinct calculations. The first two have us calculate a Ka. The first one has us do it from a percent ionization. So it says acetic acid, which we have here. We could have written HA. It forms H plus and A minus. I have H plus and the acetate anion. The first thing I'm going to do is find the percent ionization. How much A do I have in equilibrium? That's the same thing as the percent ionization. I take my original concentration, I multiply it by the decimal equivalent of the percent, and I get my amount of A at equilibrium. Once I've done that, I want to make an ice table. So initially, I have 0.0100 molar acetic acid, and just like we did in the last chapter, we assume there is no product. We have found our A acetate, and that is going to be 0.0042 molar. Think about what we did in the last chapter. When we had an equilibrium line, it resulted from us combining the initial plus the change. The same thing happens here. Since this is a 1 to 1 to 1, this is 0.0042 to give us 0.00042. Got to add another 0. Here we have to subtract a 0.0042, and we come up with a 0.0958. We do the exact same thing we would have done in the last chapter. Products over reactants. So my Ka will be 0.0042 times 0.0042 divided by 0.00958. This is the simplest of all the calculations you could do. We come up with 1.8 times 10 to the minus 5, which is the value you will find in a table. We'll talk about that in a couple of moments. Equilibrium, which is our anion. The second calculation also has us find Ka, but instead of percent ionization, we are given the pH. Let me point out, the value for the pH is the same thing as the H plus at equilibrium, okay? I wrote you can use just that equation, HA plus H plus A minus. Yes, this is a different acid, but it is a weak acid, and they all follow the same calculation methodology. So since I've been given my pH of 1.92, I will do 10 to the minus 1.92, and that's going to give me a value of 0.0120 molar. Again, pH is the same thing as saying H plus at equilibrium. So now we've set the problem up, and what we want to do is fill in the ice table. We were told 0.115 molar acid. We assume, just as we did in the other chapter, that it's going to be a 0. We've just found our pH right over here. That would be our 0.0120. Step back for a minute and say, I know how to fill the rest of this table in. I know this is positive 0.0120. This is positive 0.0120. That makes this a 0.0210. What I have to do is I have to subtract a 0.120, and that leaves me with a 0.103. I've got all my equilibrium numbers, so doing my Ka is just a matter of products over reactants. Since this is a weak acid, it is Ka 0.0120 squared divided by 0.103. Very clear calculations, okay? And my number turns out to be 1.4 times 10 to the minus 3. So both of these calculations, we're finding a Ka either from a pH or a percent ionization. These next two examples are really about concentration effects for weak acids. The last slide does the summary, but we've got to start and show you where. This is what we will call a high concentration of weak acid, nitrous acid. And it says now, determine the pH. So what I'm really looking for is the H plus at equilibrium, and the way I'm going to do it is I'm going to use the variable x. I've already filled out my table before I made my slide. I've put in my initial value of nitrous acid. I've put in my zeros for the H plus and the A minus, the anion. I've invoked what we did in chapter 15 where we used x, the variable, and then we have an expression for equilibrium. This time we are given the Ka. 4.5 times 10 to the minus 4. We will set it equal to x squared over 3.0 minus x. Now this could be very messy, so I'll explain the reason after I've done it, but I am going to ignore that x. And what I will do is I will simplify it to x squared is equal to 1.35 times 10 to the minus 3. I've multiplied 3 times 4.5 times 10 to the minus 4, and I come up with my x of 3.367 times 10 to the minus 2 molar. That x is the same thing as my H plus at equilibrium, which is my pH. So let's find the pH. pH is equal to minus the log of H plus, which is minus the log of 3.367 times 10 to the minus 2, and it turns out my pH is going to be a negative 1.434, or the pH is 1.43 because I have two significant figures. Now the reason I could ignore the x is based on a percent ionization calculation. My H plus at equilibrium was 3.367 times 10 to the minus 2. My original concentration of nitrous acid was 3. When I multiply by 100, I get a 1.12%. That number plays a role. So stop this video. If you haven't followed everything that's taken place so far, replay it, slow it down. Let's go to the next slide. This case 1, the previous slide, when I have a Ka that's approximately 10 to the minus 4 or less, x may be disregarded. You can make this assumption if the percent ionization is less than 5%. You calculate an answer. That's what we're going to do in case 2. But in case 1, our ionization was definitely less than 5%. So in our second example, I'll run it through. That's the best way to do it. So when we had our example on the previous page, we had a 3 molar solution here. Our Ka was 10 to the minus 4. The difference between these was approximately 10 to the minus 4. You can see by doing a percent ionization that it is less than 5%, so it was okay to ignore x. And we're going to be doing this later in the other chapters, so it's important to kind of work your way through this today. Case 2 is the next slide, and it says determine the pH of a much lower concentration, okay? We had a 3.0, now we're going down all the way to 0.01, the exact same Ka. So I set it up before I made this video. It says determine the pH of a 0.010 molar. It's going right in that slot. If you look at my ice table, it is identical to the ice table we had for case 1. And what I want to do is find the value for pH if I ignore x, okay? So what I will have is 4.5 times 10 to the minus 4 is equal to x squared over 0.010 minus x. Now, I'm going to ignore this x in my calculation, and when I solve for x, it will be 2.12 times 10 to the minus 3. We can say, okay, that's our H plus at equilibrium. But I already kind of know what I have to do. Let's take a look. If I put my H plus at equilibrium, 2.12 times 10 to the minus 3, I divided by my original concentration and multiply by 100, I get 21% as my percent ionization. That is much greater than 5%, so you cannot ignore X? We're going to ask this question a lot. I'm going to get a lot of questions at office hours and by email. But that is the concentration effect for weak acids. So what do we do instead? Well, you cannot ignore the X. You need to use X in the calculation. You need to use the quadratic equation. The quadratic equation boils down to look like this. This is A, this is B, this is C. Here is the formula that you need to do. You pop your values in. You go all the way down to find your X, and you find X, which is the H plus at equilibrium, which is the pH. It turns out to be 2.72. When you calculate your percent ionization, it's definitely not as large as it used to be, but that is the actual number. So that leads to the last slide in this section. Ionization increases with decreasing weak acid concentration. This is taken out of your textbook, and what it says, weak acids have larger number of molecules in solution versus strong. Take 2 points. If I go to a 0.15 molar weak acid concentration, I have about 1% ionized. But if I bring that concentration down, I don't even know what this number is, maybe 0.01, I have jumped all the way up to a 6% ionization. So the molecules are less prone to dissociate as the concentration increases, or more prone as the concentration decreases. I'm not going to make a distinct parallel, but you remember ion pairing. High charges, high concentration, lots of pairing. Low charges, low concentration, not as much pairing. Same thing here with the acid concentration. The weaker I make the acid, the easier it is for those to dissociate.